To start off, I'll talk a little bit about IML, its background. Then I'll move on to take a look at what we're planning in the 4.1 release and in our 4.x series moving forward from that. And finally, how you can get involved and contribute to the IML project. So first, a little bit of background. IML, Intel Manager for Lustre, is an open source suite of tools for deploying, managing, and monitoring Lustre file systems. It simplifies Lustre administration with intuitive interfaces and near real-time feedback. It works with new and existing Lustre installations and monitors performance and system health for those installations as well. Some more on deployment. IML allows you to deploy Lustre file systems from one centralized location. During the deployment process, you also get near real-time feedback, so you can see your file system being created, set up, software being deployed to the servers, stuff like that, all in near real time. It allows you to bring a file system online from first principles or deploy monitoring for an existing file system or a series of file systems. In addition, you can deploy specialized assets such as HSM worker nodes, and you can also deploy more assets over time as your cluster size expands. Some more on management features. IML allows you to configure or change the state of Lustre and related components. Internally, it uses a state machine to reach end states from different starting points. As an example of this, if you were bringing up LNet, the state machine would ensure that your packages are installed and kernel modules are loaded before attempting to start LNet. So by doing some, far-off operation, IML will try to figure out the correct state to move to that end state. In addition, it handles recovery situations via fencing failover, and internally uses core sync and pacemaker, and can be configured with either PDUs or IPMI. Some more on monitoring. IML has holistic system metrics. There are a series of rich visualizations. As an example here, you can see that there's a read-write bandwidth heat map for OSTs. It allows you to drill into specific file systems, targets, or servers, and also allows you to view them in aggregate. In addition, it has job stats monitoring support. So the bottom card there shows the different jobs and some statistics about them, and that's all updated in real time as well. In addition to that, we also support HSM copy tool activity monitoring and near real-time alerts to any cluster issues, which you could then view in our GUI, get email alerts for them, or programmatically through the API. So that's some quick background about IML. Moving on a little bit, we could talk about IML's development history, and IML actually has a pretty long development history. It started life as a project called Chroma, which had its 1.0 release in 2012. Chroma was developed by a company called Wham Cloud. In 2013, Chroma was renamed to IML, and Wham Cloud was acquired by Intel. At that point, there were a number of closed source releases where we did a number of enhancements. But fast forwarding to 2017, we actually had our first open source release, which was IML 4.0. Everything's licensed under the MIT license. We track against the Lustre LTS release branch. And specifically, we're trying to shift from an appliance model to useful standalone services that can be consumed individually, and IML will also go and consume those services. So that's a little bit about what IML is and its history. Now I'll talk a little bit about our roadmap for the 4.1 release and the 4.x series moving forward from that. So for our 4.1 roadmap, we had 3 high-level goals we wanted to do. We wanted to increase scalability of device detection, increase modularity of our components, and start moving towards separate management and monitoring code paths. We're targeting a GA of the second quarter of 2018, and we're expecting to have an alpha release available within the next few weeks. To achieve these goals, we've brought 4 items into scope. They are LibCFS integration, Z integration, reactive architecture, and full modularity. And I'll go through those briefly. I've included the tracking issues for each of those as well in case you are interested in checking in on their status and just high-level descriptions of them. The first enhancement is LibCFS integration. We're looking to utilize LibCFS in the 4.1 release to get fine-grained collection of pools, data sets, properties, VDEV trees, really trying to collect as much from ZFS as we can and usefully display it to the user. We think that moving in with this first step will be useful for further monitoring and upcoming management enhancements as well. And there's just some output of what we're kind of scraping out through libZFS and consuming with downstream services. Kind of in tandem with that, we also have Z integration as our next enhancement. And this also allows for discovery of data sets, properties, pools, VDEVs. But this allows for it in a more near real-time fashion. Z is the CFS event daemon, and essentially you can collect, allows you to register Zlits where you can collect information as interesting CFS changes occur. Building off of that as well, we can surface alerts in the IML GUI where we can alert for critical events, like if your Z pool went into a faulted state, for instance. We can show that in near real time. Taking a high look at kind of architectural view there, we just have a series of Zlits that emit interesting events to a persistent process in memory called the device scanner, which effectively will build up these events into a coherent view of what your ZFS file system looks like. We may also call out to libZFS if we need more information than was available in the Z event, which kind of ties in with our last enhancement. Moving on from that, we're looking to flip our device discovery from a pull-based mechanism to essentially pushing data down as it occurs. By doing this, we should be able to add further scalability while lowering resource usage and being more responsive. In our current iteration, our manager node would trigger a pull against all of our storage servers, which would then issue a series of CLI commands and file reads to try to determine the state of all the block devices and ZFS devices and mounts on the system. Given that this was pull-based, it would happen just periodically, so you could end up getting the same data over multiple ticks. And yeah, just not as efficient as it could be. In 4.1, moving to a reactive architecture instead of the manager polling. Instead, we listen to events from UDEV, Z, and FineMount as well. And whenever any of those emit into our device scanner process, we munge all that data together to build up a coherent view of devices on your server and emit that as a unified device tree. Looking at that in another way, IML creates a series of Zlits, has a UDEV run script that it utilizes, and also utilizes FineMount pull. All of those data sources have their own kind of message format that feed through a Unix domain socket into our device scanner process, which then munges everything together. Consumer processes can also subscribe to this device scanner process and get near real-time updates of the device tree as it changes over time over a single socket connection. And this is all kind of published in works standalone, so it is not specific just to IML. It's also something that's just can be generally useful. Our last IML 4.1 enhancement is modularity. And currently IML is delivered as a tarball through the GitHub release pages. So when someone wants to use IML, they effectively have to go download the new tarball version, upload it to a server, expand the tarball, run an installer script to get started. With IML 4.1, we're looking to get rid of the tarball and move all of our assets into Fedora Copper, which will enable a totally online install. Fedora Copper, by the way, is just an open platform for building and hosting RPMs. Once that's done, instead of users having to download our tarball, they just have to issue a yum install IML, and they're good to go at that point. It also enables semver minor updates via yum update, as we don't have to ship our entire product every time there's a bug fix. And moving into a service model by publishing all of these kind of standalone siloed components, it allows them to evolve independently and allows users to pull in the pieces that they feel are relevant. Of course, those who are not wanting continuous deployment can simply just disable upgrades from the repo file, or they can also perform offline installs and upgrades as well, which we have documented in our help docs. So that's kind of what we're working on in our 4.1 release. Moving on from that, we have a 4X series roadmap. These are a series of proposed enhancements for 4.1. These are not finalized in any form. These may be scoped or de-scoped, either by priority and community feedback. So we're definitely very interested in what the Lustre community would like to see in a tool like this, and we definitely will focus on whatever is most important there. We're planning to prioritize starting before our next release. With that said, our 4.2 prioritization process is going to start within the next few weeks. So it'll be good to sync up with any changes that you have before that point and get in touch with us. Moving forward, we want to target quarterly IML enhancement releases. And with that as well, we will ship as needed compatibility and bug fix releases. For instance, if there's a new version of Lustre LTS release or a OS update, we try to update pretty shortly after that. So our first proposed enhancement is enhanced deployment. We think that IML should make it even easier to set up Lustre on large-scale clusters with minimal operator intervention. And right now, IML is sort of a manual process to go through that, but we'd like to move to a point where we're using more something closer to templating to describe a cluster as a whole and expose variants as scalable UI widgets that users can configure to basically describe the variant parts of their cluster as well. Once everything has been described, they should be able to deploy our installation in parallel with a single click and get near real-time feedback of that process. Our next proposed enhancement is moving to a time series database. We think that IML should make it easy for users to consume and display statistics. To do this, we would use a popular time series database to collect statistics, which in turn would enable a well-known API and integration into third-party dashboards. Beyond that, it would also should have better performance and the ability to locate stats separately from the main database. This enhancement can be developed in sort of a siloed fashion as well. So for those just interested in monitoring and kind of a de facto reference for Lustre statistics, this could be a good enhancement there. The next enhancement we're looking at is using database change events instead of our current implementation of long polling, and basically this just falls into the vein of helping to scale a little bit better. Beyond that, we're looking to support more storage arrays as first-class citizens. Ideally, to do this, we would bring functionality in-house for well-known storage plugins and deprecate our storage plugin interface. Internally, this would allow us to simplify our architecture significantly, and it also would allow us to tightly integrate storage arrays into all of the IML product instead of having them in sort of a walled-off area. Our next potential enhancement is hardware data at rest encryption key management. And really this could be expanded to CFS encryption management as well. And basically, this enhancement would allow the user to encrypt or decrypt all drives, just a subset, the ability to store pins in a centralized store, and the ability to share encrypted pins between nodes, both for redundancy and HA purposes. Moving on from that, we'd also like to see IML have Lustre Snapshot Management. So the ability to schedule snapshots for file systems, take ad hoc snapshots, view or delete previous snapshots, roll back to given snapshots for naming snapshots, and things like taking a snapshot at key points in Lustre lifecycle, for instance, during a Lustre upgrade. And kind of piggybacking off of that, we think it would be useful if IML had full CFS management, which would include not only the ability to view all pools, data sets, VDEVs, properties, and see their status is updated in real time, but also the ability to kind of create them from scratch. And to do this, we would need pretty good ability to visualize JBOD enclosures, storage arrays, stuff like that, so we'd be able to set up devices and configurations like RAID-Z. And finally, we think it'd be useful if IML had internationalization support. So IML is currently in English, but it's used all over the world. So ideally, the way that we could enable this is to create a English.po file and post that. And this would be also a very good target for any contributions for the community, so any help is definitely appreciated there. Moving on to that, I'll talk a little bit about how you can contribute to the IML project. So IML itself is hosted on github.com. It is under the Intel HPD organization. The IML repo is located there, but also some of the collaborator services we're starting to build are also located underneath that repository. If you're not familiar with how to fork a repository and contribute to it, here are some of the steps here. But essentially, you're just going to sign up for GitHub, fork the repo, and clone it. Add your upstream and check out a branch, commit, and push. One thing to note is that we enforce that all contributor commits are signed off on. So if you are contributing, definitely use the -S flag on your commit. Once you push, just open a pull request, and our checks will run against our CI provider. We use both Travis and Jenkins for CI, depending on the repo. Once those checks pass, organization members will review and either request changes or land the change. If you're looking for an easy way to get started with IML, we have a series of issues at this long URL here that we've tagged with help wanted. These are easy ways to get started. We think they're easy to implement, and we'll offer team guidance throughout the process as well. Beyond that, you can open an issue or submit a pull request. We use the release train model in IML, so we will pull in work once it's done. If it's ready for an enhancement, it'll go out in the next enhancement release. If it's a bug fix, it will either go out immediately or through our next bug fix release. As I said earlier, we're definitely interested in community feedback on any useful enhancements to the project. So if you see anything, either in addition or any changes to any of the above enhancements, we'd definitely like to hear about it. All of our milestones are public. They're all at that URL below. So basically all the items that we're talking about, 4.4.1 and 4.x series are there. Beyond that, there's many ways to get in touch with the IML team. We're all available on gitter.im, which is kind of like a Slack for GitHub organizations. We're all pretty responsive there. Beyond that, you can request any issues or enhancements on the IML repo, like I have mentioned. We have extensive documentation on our GitHub pages at Online Help, and we also have extensive documentation on contributing to the project as well, which we kind of wrote when we went to an open source model, so it's all pretty relevant on how you can build and test and do all that stuff with IML. So in closing, IML is a project with a very long history, and it continues advancing. IML was the first open source release in October of 2017. We've had 5 maintenance updates to the 4.0 release since then. IML is targeted for Q2 of 2018. We're expecting an alpha out within the next few weeks. IML 4.2 is our next release. We're starting prioritization shortly. So any sort of feedback of things that you think would be useful is definitely appreciated within this time period. And we are actively seeking contributors, so please open any tickets or PRs for any enhancements or bug fixes. And we'd love to see you get involved in the future of the IML project. And that's it.
Thanks very much. Do we have any questions?
So you showed that you're using Fedora's Copper for RPM distribution. Have you considered using the Open Build Service to provide RPMs for both the RHEL family, the SUSE family, and then DEBs for Ubuntu?
Not at the moment. It's something that we could consider on a longer timescale. Right now, IML is Red Hat and CentOS specific. But if there was enough demand, we could certainly look at building for other platforms as well.
Are the different pieces of functionality in IML separable, or is it all kind of one big monolithic thing?
Right. So it kind of started out as an appliance, which naturally leads itself to a monolithic architecture. Now that we're open source, we're trying to split out into disparate pieces and make those available as standalone components so that people don't have to pull in 100% of IML to use it. They can pull in a portion that they feel is relevant. And at the end of the day, IML will also use those components internally to make itself work.
Excellent, thanks.
You said it tracks the latest LTS release. Are there any plans to support the latest feature release as well, so you have an option of which one you want to go to?
Maybe at some point. I think we're probably looking to get more releases under our belt and stabilize on our model.
Mm-hmm. And I guess sort of related, say you're running a 2.11 or 2.12 when it comes out, will you be able to monitor that file system with it?
Most likely, yes. I think it depends on if the location of stats and proc has changed yet at that point.